Okay, everyone. Is that better? Okay, yep, sorry. I got a slightly different setup this week, so it can get a little fiddly. Um, cool, it's alright, I'll come back. You'll hear me in a second. Yep, awesome. Okay, let me just quickly catch up. Welcome back. Thank you. Welcome. I'm happy to be back. Well, there's a lot of people in the chat this week. What's going on? We've got renewed vigor for COMP1531. The order's been slightly changed, Hemi. So I'm going to go through 9.1 and 9.2 today, and tomorrow, I think, if we've got time, we'll touch on classes. Classes are an optional sort of bonus content in the course, so we'll only really do it if if we have the time for it. Does that make sense? So this stuff we think is more important. Okay, can't hear me, that's fine. All good now, awesome, yep. Hi, still some static. I don't know if I can fix that. I'm just using a different mic, so it's probably just not as good. Because I'm down in Melbourne for a few weeks, doing some work stuff here, so that's why I've got a slightly different setup, so apologies for that. Cool. Okay, so we're running a bit behind, so we'll just get straight into the first lecture topic. But yeah, just wanted to say I'm happy to be back. I hope you had a good week with Hayden last week. Hayden's awesome. F1. I'm not here for the F1. No, that's not my kind of business. That's funny. I'm from Melbourne, so I'm just down for Easter, but I got some work stuff with colleagues from universities here, which is really good. But if anyone's watching the F1, I hope it's, I don't know, going well. I don't really know how it works. Anyway, so software complexity. The first lecture this week won't be a huge time sink. It's a fairly simple concept, I would say. Once you get your head around it, it's simple, but fairly important, and it goes along the theme with writing good code that's sustainable and well written and things like that. So we're going to be talking about software complexity, and specifically, some metrics we can use to derive an understanding of how complex the software we write is. But before we get into that, let's have a chat about what is software complexity and the different types of software complexity, and specifically the good complexity, I would say, and the bad complexity. So before we can understand how to break down complexity and to measure it, we need to have a conversation about what complex software is and whether or not it's even a good thing. So there's two broad types of software complexity: accidental complexity and essential complexity. And I think by the terms themselves, you can understand that one of those might be necessary and one of those we don't really want. And then we can introduce the topic of cyclomatic complexity measurements, which is a really complex way of saying it's just basically a formula we can use to measure one metric that we can use to measure how complex potentially complex the code that we write is. But let's break down sort of this software complexity in terms of accidental and essential. Before we do that, in 1986 there was basically a position paper written called No Silver Bullet, The Essence of Accidents in Software Engineering by Fred Brooks. What he's basically saying in this paper, there's a link to the paper in the next slide I think, but I think the link's broken, so I'll just find it in a second. But what he's essentially saying is that there is no silver bullet to help us write low complexity code. And by low complexity, what we mean is code that solves the problems that we need to solve, but without being overly complex that causes problems and things like that. So basically he's saying that nothing's going to really come along. What it's really about is hard work from software engineers like yourselves to write good code, scalable code as you go. But this is where the introduction of the two terms essential and accidental sort of start to take wind. So the idea being that there's some complexity in the code that we write that's just, we can't avoid it, right? The problem that we are solving has a nature of complexity, therefore the solution that we write has to conform to that complexity. And so the code itself would just be complex and there's nothing you can do about it. But then there's this idea, well, and I think this is most of the complexity we have in software, it's accidental. And what we mean by this is that it's actually a fairly simple problem we're trying to solve, but we don't have a clear picture of all the different ways we can solve it. So we end up writing just one of the solutions, and that may be needlessly complex. And this is a bad thing, right? Complex software is bad. If every program we could write was as simple as possible, we'd all be much happier. We'd have less bugs, less failures, and things like that. Why is that? More complexity, more code, harder to understand, more places that can go wrong. You get the idea. We've spoken about this for the past 9 weeks. The simpler solutions that we can build, the better, always. But sometimes we can't avoid a complex solution, and this is this essential complexity idea. There's other ideas in the paper, and it was a long time ago. Some of these ideas have been argued and things like that. But essentially here, again, just to break it down with another slide, essential complexity that is inherent to the problem, we can't avoid it. If the user requires the program to do 30 things, the 30 things are essential, we can't avoid it. But then there's this accidental complexity where, it's not inherent to the problem, and we've just built it in maybe accidentally over time. So programmer 1 jumps, this is what really happens a lot, I think. Programmer 1 jumps on a code base, writes a nice solution for something. A few months later, or a year later, software engineer B comes onto the project, needs to slightly extend or modify the solution, doesn't have the best understanding of it because they didn't write it, they didn't put the time to understand it in, so they hack on a solution, but the solution might use some other libraries to do something that a previous library could have already done, and now you've got a slightly more complex program. And if you take that idea and multiplicatively apply it, you can understand how very quickly and very simply we can snowball out of control and have these wildly complex programs that aren't actually doing much, and they're needlessly or accidentally complex. I spoke about this a few lectures ago, but I always think about one of the software engineers I used to work with who told the story of their first software engineering job. They were an intern for a big Australian company that had a software team, although they're not well known for their software. But first job, he walks in and on Monday morning, the software engineering manager says, can you look through this program? There's like a bug in this file. We don't really understand it. We haven't put anyone on it. It's not that important, but could you take a look at it? And this person, really good software engineer, spent, I think, over a week, trying to get his head around the software. It was really spaghetti codey and all that stuff. And then finally, at the end of the week, realizes that actually none of that code was even executed. It was all just sort of bloat that was left there that looked like it was sort of being executed, but it wasn't really. And this is, that's another example of this accidental complexity. And the more novice a programmer you are, the more accidentally complex you're likely to be. It's really common. So essential complexity, again, fundamentally can't be removed, but it can be managed. So if we write it well, it'll be still clear what's happening, why it needs to be there, and we should all be dandy. And hopefully with good practices, like some of the things we've started teaching you in this course, you can start to understand how we can mitigate or avoid writing accidental complexity in the first place. But, you know, it's really hard to remove entirely. Why is that? Because software evolves over time, many people work on it. You don't have really one person in a complex enough software system has a full understanding of the entire, system. So it's not clear to say that, well, all this code can be removed and refactored into a few lines. I mean, really good software engineers will do that, and you will do that. But it's really hard to do because it's scary to break things and then rebuild them slightly better. In some ways, it's almost safer just to say, look, yes, it's complex, but it's working. We just leave it. And that's the thought sort of process or trap. It might be a trap that engineers fall into that leads us to having these complex and bloated software systems. You see it all the time. So there's a lot of discussion about this stuff. People write books on it. People try and build tools to solve it, PyLint and things like that. And here's, some open questions. How do you distinguish between accidental and essential complexity? How much of modern software complexity is accidental? And to what degree has accidental complexity? What degree will it be removed in the future? You can try and answer these questions. You're probably not going to come up with any good answers. But we can start looking at some metrics and some tools and some things we have, some solid thinking that the industry has come up with over the years to deal with complexity. So here's some of those links. Like I said, this silver bullet paper is not working, I believe. But why don't we just try and find it really quickly. Here we go. This looks like it's it. I'll put it in the chat for your, I know this is what you'll be reading for leisure. And then we have a more modern description. Okay, and then we have a rebuttal. So actually, I wanted to talk about this a little bit. And again, if you've got any questions about this stuff or prompts, just put it in the chat and I'll get to it when I can. But so this person in 2019 basically wrote a rebuttal paper, which if you're not, you get the idea what a rebuttal paper is, but it's where you take a paper that's been published that you might have some disagreements with and you just write a response. And this person, Mark Seaman, is saying that actually, I don't agree that there are no silver bullets to help complexity. In fact, I think there are some, and this paper sets out about responding. So here's the original sort of quote from the No Silver Bullet paper. There is no single development in either technology or management technique which by itself promises even one order of magnitude improvement within a decade of productivity, reliability, or simplicity. And then what this person, there's a bit of a breakdown here, but what the interesting part is down here is 3 honorable mentions of maybe things that this author is suggesting are silver bullet-esque, right? So he's saying himself, I'm not going too far, but for example, Git has made software engineering much more productive, and that's why it's extremely cool that you have all used Git in this course and you're actually quite familiar with it for first year software engineering or computing students. It is really impressive, but the amount of effort that used to, still does go into source control, but that used to go into source control that took away from development productivity, means that Git has been a big push for software engineering productivity. There's a lot of reasons for it, basically, but just how well it works and how reliable it is means that people have trusted it. So people aren't, like this author is saying, for example, people aren't writing commented out code just to make sure it's sort of stored and backed up. They're relying on the branches and putting work in progress code on another branch and pushing that to a repository so that it's stored. And people trust the system, so they're not worrying about it, which means they can just get thinking about the feature that they want to build. So Git's been a big productivity boost. Garbage collection, I don't know how much you guys have actually sort of specifically been exposed to garbage collection. Does anyone, do all of you know what the term roughly means in software engineering? Not in terms of, what your council does once a week, hopefully, or every 2 weeks. We're getting a 4th bin just for glass. I mean, it's good for the environment, but I don't have room for a 4th bin. Ask your keyboard if it wants to be shot. Yeah, it's a different keyboard, as you can tell. It's quite loud. I need like a AI background noise remover. You know what makes Minecraft run faster? I mean, I guess so. Minecraft runs in Java, right? Java is a garbage collecting language. Does anyone know what garbage collection is? What is it? Cool. I mean, awesome. So 1511, you wrote C, right? C is not a garbage collected language. So what that means is that if you request some memory, right? So if you call malloc in C, the C programming language asks the operating system for some memory. Yep. And you tell it how many bits or bytes of memory you want. Makes sense. The operating system says, sure, here's some memory that's on the stack, do with it what you want, put in it what you want, go nuts, and it hands it over, and then that's it, right? Now, if your program, the function ends and you continue on, and you never call that code again, right? That memory is still just going to stay there. You've still your program has still got control over that memory on the heap. Because you never, unless you specifically or explicitly clear that memory, it stays associated with your program. Does that make sense? This is why we have memory leaks in a lot of the time in C and C++ or non-garbage collected programs. For every piece of memory you malloc, you need to dealloc or free the memory explicitly, and you need to free the exact same amount of memory at the exact same pointer position. Right? So you request the memory, you get the memory, but you need to free the memory at the end. And if you forget, and then you malloc some more memory, and then you malloc some more memory, you've got a memory leak. That's what a memory leak is. You keep asking for more memory, but you're not deleting the old memory that you no longer need access to. Now, the reason why C and C++ do this is because the languages are all built away. Well, back then I think garbage collection didn't exist as a concept. It might have, I'm not sure about that. But even today, if someone was to come and rewrite C from scratch, they probably wouldn't put garbage collection in the language. The reason for that is that in those types of languages, the idea is about giving all the control to the programmer. So the idea is that the software engineer is the person who should decide when to malloc the memory and when to free it. And they'll do that when they think it's best. In the push of object-oriented programming languages and programming languages that were designed to solve bigger scale programs or problems, we're getting, we're not doing operating system levels, or hardware level engineering anymore. We might be solving financial institution problems or websites and things like that. So we got an abstraction of software languages, and the idea was that, well, do we really need the software engineer to manually keep track of mallocs and deallocs and all of that stuff? What if, as the program that is running, something called the garbage collector comes and every so often has a look through the program and says, ooh, there was some memory allocated here that's actually no longer referred to. which means it can never be cleared or used again because there's no references to it. I'm going to just clear it for my program. So it's like a program running in the program that looks into the memory and says, oh, this memory's not used anymore, this isn't used anymore, this isn't used anymore, and deletes it. And every so often, it looks and checks for any unreferenced memory. That's a very, high-level explanation of garbage collection. Now, the upside is that you don't have memory leaks. The downside is that it takes computational power to run the garbage collector, right? So in some cases, the software might not be as efficient because the garbage collector has to boot up, look at all the memory, and then it might not even delete anything, but then it has to stop. But that still took efficiency. But for most general purpose programming in Python, in Java, all of that, the garbage collector solves more problems than the efficiency hit that it takes, especially with modern CPUs. They're just incredibly fast. So garbage collection is awesome because it meant you don't have to worry too much. I mean, you still should be thinking about your memory, but you don't have to worry as much about it. Garbage collection just makes this work go away. It's hardly a tenfold improvement in productivity, but it's significant. I agree. Ooh. And then the final point on this topic of big productivity boosts in software engineering, right, is agile software development, something that you've sort of been doing with the projects. In fact, you have been doing. You've been doing sprints in your project. You've been using the board to plan work. This is all ideas that come from agile software methodology. We've already spoken about these methodologies. We're not going to go back and compare waterfall to agile, but this author is saying that in their experience, they've seen a big productivity boost from working like this with software. And again, I agree. And so it's kind of cool to take a look together as a course in 1531 with all of you who, most of you are relatively new and up and coming software engineers. But to take a look back and see, how did we get where we are today? How did we get so efficient? And this author is saying, actually, there were a few silver bullets that helped us get here. Languages, things like Git, garbage collection, etc. So, very exciting. Any questions on this stuff? Okay, I think I don't need that. You're shivering from Malik, fair enough. I have no idea what Tejas is saying. Sodium, phosphorus, anyway. Cool. So, that's software complexity. That's how we've been trying to deal with it. How can we measure software complexity? Well, there's a few ways. Coupling is a term to measure how closely connected different software components are. So this is usually just a simple measure of how loosely or tightly software components are coupled. So for example, web applications tend to have a front end that is loosely coupled from the back end, and loosely coupling is good. So let's break this down a little bit. No, there's no more to break down, so let me just break it down. Take two components of software in the one system. Now, this could be, like this example on the slide, a front end for your Seams app and a back end of the Seams app. These are two software components. In fact, they're two separate programs in different languages, right? You've got the Python back end and the web front end. And we can basically measure, not scientifically, right? We can just think about it because we're all incredibly intelligent human beings. We can just think about, how coupled is the front end from the back end? What is the connective tissue that joins the front end from the back end? So, I'm asking the chat, so right now, just think about it. When you run the Seams back end with the front end, what's happening in the middle? How is it coupled? How is it coupled? Shang says, magic. Oh, we've not done a good job in 1531 there. I know, he's joking. Blue Play says request, which is probably the closest answer here. David says the cloud. I mean, not really, because it was running all locally on your computer, right? So it doesn't have anything to do with the cloud. That might have been a joke, I'm not too sure. But interface, Paul, that's really vague. Everything's an interface. I'm interfacing with this water bottle right now, which is a really disgusting way to think about it, but I am. Echoic says loose. I agree it's loose, but that's not what I mean. I'm not saying how coupled is it. I'm saying how is it coupled. Julia says requests following the interface. Yes, but you're all still being a little bit broad. Echo, guys, we have an echoic and an echo. Echo says an API. So does Hemi say the API. Absolutely, you're all on the right track. We have a HTTP API on the back end, and then over the network, API requests are sent, and the server responds back via HTTP. So really, HTTP, right, is the coupling. So is this loosely coupled or is it tightly coupled, and how do we know what the correct answer is? I mean, it is a bit subjective, but I think it's loosely coupled. Why? Because the front end really has absolutely no idea about the back end, and the back end has very little idea about the front end, right? The back end doesn't know how big the front end is, what language it's written in, what it looks like. Really, it's got no ideas. And the front end, if you look at it, it doesn't know what server the backend's running on. It doesn't know what hardware the backend's running on. It doesn't know what functions the backend. It just calls the API via the HTTP interface, and it gets some response. It's a black box. Yeah, the front end doesn't know what the back end does. It just knows here's what I should call and here's the response I should get. That's why it's very loosely coupled. If you could imagine that the front end, let's say it had to know the name of the functions in the Python backend, right? That's very tightly coupled, because now if the backend changes, the front end's going to break. If I rewrite the backend in a new language, the front end might break. Do you guys agree that? Do you see it? Do you see what I'm saying? Are you picking up what I'm putting down? The backend and the front end in the Seams app that you're building in the iterations are loosely coupled. And I mean, that makes sense because HTTP is a protocol for black boxes sort of communicating. But it's not just, two separate software systems running. It can be two functions in a program, right? If you've got two functions that do different things, should they rely on each other or even the existence of each other? No. But if they do, like if one function calls the other, waits for the response, and they both call each other, then they're tightly coupled. So the last question I'll ask on this topic is why do you guys all think loosely coupled software is good? Am I really dark? Oh, I am. Better? Julia, it removes non-essential complexity. It'll be easier to do maintenance if things break. Yeah, absolutely, guys. Exactly. You guys get it. You don't have to, if you fix something in function A, you don't have to go and update functions B, C, D, E, F, G, all of that stuff. Exactly right. Yeah, you're all getting it. I'm just going to turn this on. I don't know if it's going to help. Probably not. Okay. Yeah, cool. You guys are getting it. So whenever you're writing software, always think if you've got two components, do these need to be as coupled as they are? Okay. Another sort of concept or idea is this concept of cohesion, which is referring to the degree of which that elements of a module belong together. Okay, so elements belong together if they're somehow related, and this is usually expressed as a simple sort of low or high cohesion, similar to tightly or loosely coupled. But high cohesion is good in this example. We're not going to go too nuts with this, but let's just have a look at, this was a really good Stack Overflow article. I'll get you guys the link. Here you go. So this is probably worth a bookmark. But so let's look at some examples here. Cohesion refers to what a class or a module, now we haven't spoken really about classes and objects too much in this course, but you don't have to really worry about it. But you've got some software module, and you have organized your code into, these sort of properties. So for example, let's look at the high cohesion example first. So for example, you have some software module that represents staff, whatever staff means. So staff might have a salary, an email address, a name, whatever. And then you look at what are the things that a staff module can do. Well, you can read that salary, you can set that salary, you can get an email address, maybe you can email them, maybe you can do things like that. But all the things in that module are only related to the broader concept that's contained in that module. So if we look at an example of low cohesion, why does a staff module need to, validate an email address? That doesn't sort of make sense. This belongs more in like an email validation module or a helper module or something like that. So cohesion's all about, if you've got, a module or a block of code or a section of code or a file even a file. Here's another example. Let's go back to the seams application. Why do I lose the tabs when I'm in full screen? If you go back to your seams application and you've got a API module. So you've got a file with all the API endpoints in your program. And then at the end of it, you've also got some non-API function that can, do the authentication. Does that make sense? Or should that content, that authentication code be in another file, right? You're now mixing the cohesion. You're lowering the cohesion of your project. So you want things that are related to each other to be next to each other, but then everything else should be somewhere else. Does that make sense? It's like an organization. It's where you put things that need to exist. So we're not saying these things shouldn't exist. They need to be in the program. But cohesion is all about where they live. It's a pretty simple concept. Any questions on that? Did I explain it okay? The Stack Overflow article is quite good. I'm just looking at the chat, making sure. I'll keep going and then I can come back. Okay, and here's the big bad of today's lecture. Cyclomatic complexity. It's a pretty scary term, sounding term. It's pretty cool. I always thought it was a cool sounding, cyclomatic complexity. I don't know. It's got like a cool air to it. But it is a metric used to measure the complexity of a block of code. And that block of code could be an entire program, a function, a module, or something like that. And the fancy definition of it is the linearly independent paths throughout a function. But when we really break down what it's doing and what it's measuring, it's really not that complex. But it measures the branching complexity of functions. This is the cyclomatic complexity function itself. So the score is equal to the number of edges minus the number of nodes plus 2. And there's a reason for that plus 2 that I may or may not remember and I may or may not explain. But basically, you've always got a start and end. So you have one, I think it's one for the start, one for the end. You know, like you've got to enter some code at the top, right? You got to exit at the end. So you've always got a static 2, I believe that's why the 2's there. And then the rest is just the edges minus the nodes. So let's look at some examples here. So here's some Python code. I don't know how well you can read it. Is it clear? I don't know if I can zoom this. No, I can't. Hopefully it's clear. I mean, you should have all the nodes for this anyway, but it's a really simple program. I mean, it's not even, I don't even call it a program, but you've got a function called foo. If some condition A is true, do B, else do C, and then always do D, right? Nothing crazy here. And so if you take a function like this, you can turn it into a graph, which is what we have here on the right. So here we have that branch A, the vertice. And from that branch, there's 2 potential outcomes, right? We can either, depending on whether or not A is true, we can either do B or we can do C, right? And that's literally what this graph is demonstrating here. We can either go from A to B or we can go from A to C. And then we always go to D no matter no matter which path we went down. So we always end up at D. Make sense? Nothing mind-blowing here. And then we just plug in that formula. The number of vertices, sorry, is it vertices? So edges, yeah. The number of edges, which would be 1, 2, 3, 4, right? The lines, minus the number of vertices, A, B, C, and D, so 4 minus 4, plus that static 2, because you had to enter at the top, you had to exit at the bottom, and we just sort of assume that we have to do that, will result in a cyclomatic complexity value of 2. That's it. That's cyclomatic complexity. You can do it by hand. I mean, we've just done it really by hand, sort of. It's not even really something that you need some fancy tool to do. We can look at another example. Here we have, so if condition A is true, do B, else. So we have a nested if here. So if C is also true and A is not true, this is what this is saying, then we can do D. And so we can turn this into this diagram. Oh, and then at the end you do E, right? So we turn this into this graph and we're just visualizing the paths throughout the program. So A can either go to B, which goes to E. That's pretty similar to what we had before. Otherwise, A can go to C, optionally can go to D, always ending up at E. Now, with that, I mean, I wish I could sort of hide the complexity calculation, but without even looking at this complexity calculation, which program is more complex? I mean, if you're paying attention, and I know you all are, the answer is example 2, right? There's just there's more potential things that could happen. If you're reading this code, if you're writing this code, there's more to keep in your short-term memory. Agreed? And the cool thing is that when we plug this function into the cyclomatic complexity algorithm, we get a higher complexity. So again, the number of edges, 1, 2, 3, 4, 5, 6. So edges are just the lines between nodes. Subtract the number of vertices, 1, 2, 3, 4, 5. Plus the static 2, we get a complexity of 3, which was 1 higher than the complexity of example 1. Here's another. Am I going too fast? I should pause for a second. Am I going? Are we all happy as of example 2? Please don't make us count dots and lines in the final exam. Are you sure? What if the whole exam was just doing this over and over? For like 3 hours, you just kept calculating complexities. Wouldn't that be a good time? Yeah, easy marks. In that case, I mean. Yeah, exactly. At what cost? Exactly. Yeah, cool. But so, yeah, exactly. You could put on the stream music. So are we all happy as of example 2? Is this making sense? All right. Cyclomatic complexity is not this super complicated idea. It's just that there's a certain number of paths in a block or a module of code, such as a function, and the complexity number is associated with how complex from the outside looking in that code really is. Let's look at example 3. So example 3 has a loop. So while A is true, do B, otherwise do C. We can represent this the same way in a graph. A can go to B, B goes back to A can go back to B, B goes back to A, and then finally we do C following A, right? Not following B. The interesting thing here is that this loop basically does not increase the cyclomatic complexity of our function. And the reason for this is that there's no extra paths throughout the program. So even though A can go to B and B can go back to A continuously, there's not, it doesn't matter if you call B 1 time, 10 times, or 100 times, there's only one B and there's only one A. So the complexity doesn't keep stacking. That's what we're trying to communicate here. So again, if you plug the formula in, you'll get a pretty low complexity score of 2, right? So number of edges, 1, 2, 3, 3 nodes, therefore we get a score of 2. Okay, here we have a slightly more, complex program, day to year. So this is a real sort of function in this case now. The year is 1970, while days is more than 365. Basically, we're counting up the days. I'm not going to run through the code line by line, but again, we can turn this function into a graph, right? And then we just do the counting, we plug the numbers in, and we get a slightly more complex score of 4. Yeah, this is just a slightly more complex example. And then one more here. Okay, so what we're trying to talk about here is, so we've rewritten the same program, and it's probably better to look at the notes for this to sort of compare the code. But this is something that actually pops up a lot, and I see this spoken about a fair bit. But sometimes by rewriting how we can, structure a problem, we can sort of lower the complexity of the function. So in this example, we start by checking is the day is greater than 365. The answer will be no. And then we subtract a year from days, it looks like, and then we add 1 to the year. And we get a complexity score of 4 with this example. But by restructuring it and, days is passed in, that's what was confusing me just then. Gotcha. So that's just the integer count of the number of days that we're converting to years. By restructuring how we can write it, this function solves the same program in the problem in the exact same way. And by looking at the code, it's kind of clear that this is simpler than example 4. There's just less lines of code. But it's also cyclomatically less complex. And by converting it into the graph, we can see that. And by calculating the score, we can see that. So the cool thing about this example is that it's a demonstration of how we can actually use cyclomatic complexity as a hardwired metric to determine if changes to a code base result in a more or less complex solution. And again, the lower complexity is better. So some takeaways from this. Here's the important part, right? There's no point going over and over how you can calculate the complexity. Basically, what people argue is that, you know how you've probably heard that people say, you know, who is people? I mean, I don't know, people on Stack Overflow or something. That there's a maximum number of lines a function should have. It's about, I don't know, I can't remember. In the clean code book, I think it's like 15 or something like that. But why don't we quickly just... okay, 50 to 60, I was way off. Oh no, 10 to 20 methods, 50 to 60 lines roughly. I mean, it's depends on the language and who you're talking to, for example. But there's some, you know, thought tank sort of ideas into how many lines should be in a function. And there's the same sort of thing for how complex a cyclomatic complexity score should be, with the maximum being somewhere between 8 to 10. Any more than that, and your function is just too complex, and it might be better to break it down into maybe separate functions, or have a look at the algorithm to see if it can be improved or something like that. Now, cyclomatic complexity is, like everything we talk about in this course, is not a silver bullet. I mean, this is going back to what that original paper was talking about. It's not going to make your life easy, right? It makes some assumptions, for example, that non-branching statements have no complexity. So if we called function A to check if it was true or false, we don't know what A is doing. It could have 100 branches, for example. The other drawback is that one of the ways that people try and keep complexity scores low is by splitting functions up, so functionally decomposing their problems. And that does reduce the score within a specific function, but it can actually make the whole file more complex to read. So it's just an example where, with experience, you will learn when to make the call, when to ignore the score, when to, you know, lower the score, for example. Okay, and that is lecture 1. I think the last slide, oops, what did I just do? Oh, yeah, of course. And like everything, in PyLint, there's a optional module to PyLint that can calculate cyclomatic complexities. The big caveat here is that depending on the implementation and whether or not you're doing complexity calculation manually or through something like PyLint, you might actually get slightly different results. And this is basically because of how it's building out those graphs. But you don't really have to worry about it. As long as you pick the one tool consistently, you can sort of refer to it. So, I'll just bring up my little, that's not what I wanted. Oh, I lost it, damn. Okay, I can just bring it back. Okay. Now you probably can't even read any of this, so let me come like this. Let me make that bigger. All right, so we've got a program here, a function called F10. We don't even call the function. You can see there's a lot of branches in this. When you see a lot of branches, you're going to be thinking high complexity score. How do you run? Oh. I've lost it. Okay. I did have this and then I've just, here we go. So I think we can just run this. So you run PyLint, you give it the name of the program. So in this case, I've called it pylint.py for some reason. And then, now by default, PyLint doesn't calculate cyclomatic complexity. So there's this parameter here, load plugins, PyLint extensions. Bad built in? That doesn't seem right. Okay, let me just PyLint cyclo. Oh, it's called macabre, I think. Not McCabe. So McCabe is the name of the researcher who designed the cyclomatic complexity algorithm. So Pylint have called it. Here we go. That's what I wanted to do. So it's load plugins. Whoops. Pylint McCabe. So again, the McCabe score is cyclomatic complexity. And I think if that works, we run that. Here we go. And so you can, the cool thing about this is there's a bit to break down here, but it's calculated the cyclomatic complexity. And I believe it's come up with a score. Where does it tell you here? Oh, no module named Pylint Macabre. So maybe I need to install it. You do. Okay, so it's a pip module. Okay, it still says no module named, but interesting. I just tested this before. What have I done? Oh, you need to load it. I see. In Pylint.conf. Okay, let me quickly just do this. All right. What if we run this now? No module named load plugins. No module named. Oh, -- load plugins. It might not like that it's called Pylint. Oh, there is no Pylint. Oh, no, I'm at the desktop. That's fine. Sorry, guys. Sorry. I shouldn't have been working from the desktop, I guess. Maybe it's better that I just... In 9.2, okay. We have the Pylint there. All right, so I'm just going to make a new file here. I'm just going to call it. I don't want this to be in the. I want this to be in content lecture code, and then I can push it up for you all. Sorry about this little delay. 9.2. Oh, I didn't want to call it that. I'll just call it F10. That's fine. No. What have I done? Oh yeah, that is what I wanted. All right. No, never mind. Okay. Oh, okay, I've got a file called f10.py. In the same directory, I've got this pylint.conf file. So I think now I should be able to just run pylint f10.py. And then it's... I've lost it. Load plugins, Pylint McCabe. Why has it done this? Oh, whatever. It's still saying this fatal error while checking file f10.py. If anyone can get this running before me, that would be good. Pylint McCabe. Anyone have any ideas? Or is it just working the first time? Yeah, I think it is just working there, to be honest. Let me just close that. Okay. I think this is saying it's getting a score of 5.6 out of 10. But this is summarizing. Because what does this say here? Introduces a new warning, too complex, which is emitted when the code block has a complexity higher than a pre-established value, which is controlled through the max complexity option. F10 is too complex, the macabre rating is 11. Yeah, so ours is not doing that. So something's wrong with this module here. Maybe it's just not installed properly. But I mean, I'm not going to spend too much time on it, but you can have a look at... It's saying it? Am I just blind? I'm not seeing it. Oh, it's right here. Oh my god, sorry. I thought it was going to be at the end. Sorry, everyone. Yep. So the macabre rating is 11. So basically it's doing a bunch of different things, but one of them is determining the cyclomatic complexity, calling it the macabre rating, I don't know why I'm calling it macabre, and it's giving it a score of 11. And that's saying it's too complex because we have set the max complexity to be 10. So you can, and then again, thinking about what we use Python for, this could be running on your GitHub pipelines and saying, well, if someone pushes a function more than 10, maybe we don't get rid of it or we have to look at it, but maybe it's just that we need to put some eyes on it and make sure that it was something suitable and that it's suitable to be as complex as it is. Cool. All right, sorry about the quick run around there. How is that all sitting with us? Now, someone in the chat asked a really good question. Excuse me. Where is it? It was about the labs. About Friday. Oh yeah, Tom, here. I just thought of this, but what am I supposed to do if my tutorial is on Friday, since Friday's a public holiday? Great question. I'm making an announcement on it today. I've been working quite hard behind the scenes on coming up with a good solution for this. The short answer is that Friday's a public holiday. The university does not reschedule classes on a public holiday. So there's not really a nice solution. What I'm going to be doing is a bunch of things. One of the tutorials this week is going to be, one of the online tutorials is going to be recorded, and that will be made available to everyone, even if you're a campus student, a non-Friday student. So you can watch the first tutorial and sort of follow along in your own time. The second thing is that I think most tutorials on Friday will actually run as an optional help session thing. So they're not going to be mandatory tutorials because it is a public holiday. You don't have to go to them. But a lot of the tutors have kindly agreed to just run it anyway. And they won't be proper tutorials because then it's not fair that other people miss it. But it'll be sort of like a private help session. So you can just drop in and you can still talk about your project with your group, with your tutor, talk about your labs and sort of get help and whatever. So there's that. And then also you'll be able to attend another tutorial, another online tutorial, not a campus tutorial, if you wish this week. So with those few things together, I'll lay it all out really clearly in the announcement that I post. But you'll be able to do everything you need to do this week if you're on a Friday tutorial. Does that sound good to everyone? I mean, so short of it is you don't really need to worry about it. If you're free on Friday and you're not doing anything, you can just go to your class, and your tutor will make it clear whether or not theirs is running. Otherwise, you can just watch the tutorial and work with your tutor asynchronously. Yeah, it was a tough one to sort of solve. I know some other classes just cancelled all classes for the week, but I didn't really want to do that. We don't have enough time anyway, so. So Justin, there's no private help session link. It's what I mean is that your pre-scheduled tutorial will just sort of be a help session-esque thing. Really, what your tutor does in that time is up to them. I'm not prescribing anything. So it's just the normal Friday tutorial link that you've been using all term. And it's only for people in those Friday tutorials. So if your tutorial's on Thursday, you just go to your tutorial on Thursday. Ooh, good point, Sienna. Yeah, I'll move it to Tuesday because Monday is also a public holiday. That's a great point. Yeah, I'll move it to Tuesday. I'll put that in. I'll have to write this down. I'll put that in the announcement. All right, I'm gonna go make a coffee, and then we'll be back for the next, for 9.2, the second lecture today. Yeah, feel free to write any questions about this stuff that you got lingering in the chat while I'm gone, and when I come back, we can jump in and answer it. Let me. No, that didn't want to work. Let me get the beats going again. Oh, they're already going, so I just need to come here. Alrighty. Ignore the 8 there. As you know, we did some reshuffling with the lecture series, but we're all back. Oh, I've lost the chat. Okay, cool. How's the numbers looking? 53 students, awesome. Alrighty, we good to go? We have 45 minutes. Plenty of time. Week 9, lecture 2, or lecture 1, part 2, safety and type checking. So this is all about writing, good, scalable, secure software. So we write code, we try and do our best, and there's sometimes we do some work, and we implement bugs, we cause programs to crash, we do things slightly wrong, we don't think things through properly, and we have a bad time. So what we're trying to do in this lecture is just have a discussion around some of the characteristics of programming languages and how these languages try and help developers prevent bugs. Pretty cool that these languages are sort of helping us out. 4 specific topics: software safety, memory safety, runtime error safety, and type safety. Now, this isn't talking about security at all, and this course doesn't really talk about security, we just touch on it. But it's talking about sort of tools, practices, techniques, language features that helps us write code that is less prone to certain types of bugs and crashing and patterns and things like that. It'll make a bit more sense when we get into the nitty-gritty of it. But as a bit of a definition here, safety is the protection from accidental misuse. So you write a bug that makes the wrong, you write some code that makes the wrong assumption about a function, for example, and when you call it, rather than just exploding in a pile of flames, if the code is a bit more safe, it will maybe warn you or not let you do it or something like that. Security, on the other hand, is protection from deliberate misuse. There is a relationship here. More safe code is probably more secure, but it's not a one-to-one correlation. So software safety is all about writing code that's designed from the bottom up to not be able to be misused, both intentionally and unintentionally, but mostly unintentionally. So it's either allowing and accommodating for unexpected behaviors, maybe future-proofing, and it's also responding to when this happens in a more, graceful way is the word I was looking for. Some really quick examples, right? You remember in 1511, you're writing a C program, you've got an array, you maybe loop one too many times and you read add an index outside the array. You've all done this. What happens? You get a seg fault. The program tries to read some memory. The C code asks the operating system, hey, I'd like to read this sequence of memory. The operating system says, whoa, you don't have access to that. That's not your memory. I need to now take you out the back of the, yeah, I'm not going to go down that analogy. The operating system kills the program. Why? Because it did something that it's not allowed to do. It tried to read memory outside of what it's allowed to. Why is that a problem? Because then you have security issues, because you might be reading memory from another program. That's not allowed, right? So that's why when you read from an array potentially outside of the initialized memory, the program might just crash in a seg fault. Or you might write outside of array boundaries or something like that. Same idea. And if we look at why these sort of things happen, there was an interesting case study on spreadsheets, which found that about 94% of spreadsheets contain some sort of error. And for any given spreadsheet formula, there's a 1% chance it contains an error. That's pretty cool. I guess that says that there's 94 formulas in a spreadsheet on average. Is that right? So, but why is this the case, right? Why are people writing such problematic code? You might say, well, the type of users writing spreadsheets formulas are not they're not software engineers, they're not trained. You might say it's because of the frameworks around spreadsheets. They're not really built, spreadsheet formulas is a form of software development, but they're not languages and frameworks and pipelines built around safe code. So it's very easy to write formulas that aren't 100% correct. And there are some tools and methods and frameworks to detect and to prevent these sort of problems. Static and dynamic, we've spoken about these in a previous lecture. So static properties can be inferred without executing the code. So you basically look at the code and you try and infer some information about the code. So pylint is the classic example here. But we have spoken about this in previous lectures. And then we have dynamic ways when you actually run the program. And then when things are happening during the execution, you can try and be a bit more graceful or determined. For example, in Python, when you use an index inside to access a list element that's outside of the maximum length, Python actually, it doesn't throw a segfault like C, it actually throws an exception, the difference being, so they would both just result in the program crashing, right? But in Python, you threw an exception so you could catch it, whereas C, you can't really do that. Does that make sense? So Python's giving you one last opportunity to say, hey, you weren't meant to look this far ahead of the array. I'm not actually going to look. I'm going to just throw an exception, warn you, and then if you don't do anything with that, I'm going to crash. Whereas C actually tries to look and then the operating system kills it. Do you see the difference there? I actually want to jump ahead a few slides. I'll do it in order actually, and then I'll come back and talk to it. But just keep that in mind. So how can we remove or detect or prevent errors statically? Well, we use things like PyLint that warns us, maybe after we write the code, but before we commit it, that something's gone wrong here. So maybe we're using an unknown identifier, right? And then you haven't even run the code yet, but statically you can look and you can say, there's no variable called X, so don't bother, right? And this happens in C too. When we run the compiler, it will say, no, I'm not even going to compile this. I'm not going to let you run it because there's no function called Y and you're calling it, right? So C does still have some static analysis to determine errors. Here are some examples. In C, for example, reading from memory that's not been initialized, dereferencing a null pointer, that's always a problem. Using memories after it's been freed, writing outside the bounds of an array, and forgetting to free allocated memory. This one's a bit, I mean, it's not really, it can cause a problem if it stacks up, but it's not going to initially cause a problem, right? We have the same sort of things in Python, using a variable that hasn't been initialized, accessing a member of an object that we don't have. So you've probably seen this all the time when you get a key error. Like you use a key to look up a dictionary value, but the key doesn't exist and the value doesn't exist. Or you pass a value, passing a function, a type of object it doesn't expect, right? And then it tries to do something with the parameter and it fails. And again, we're talking about what some languages do to make the runtime environment more safe. And C is a good example to compare against because it's the least safe. Just like when we spoke about the garbage collection, C doesn't have garbage collection. C is all about, you've heard this analogy before probably, but it's giving the programmer the shotgun and letting them blow off their foot. C is all about giving all the tools, removing all the boundaries, all the filters, all of the capacities and things, and letting the programmer do everything. So it will let you try and check an array outside of its limits. It doesn't even know about the limits. When the operating system, kills a program, well, you're kind of screwed, but you shouldn't have done that in the first place. It lets you try and dereference a pointer, even if they don't point to allocated memory. So it's prioritizing performance over pretty much everything, right? That's why it's good for operating system development and things like that, because the code is well vetted, so you can make sure it performs well and that it's secure and safe. For runtime errors, right, so dynamic errors, different languages have different conventions for handling these errors. So if we look at Python, for example, here's a key error again. We look at the fish key in the animals dictionary. If fish is not a valid key, Python throws a key error. The reason it's throwing the key error is that it's allowing the developer the opportunity to detect that raised error and handle that situation. But C does not support exceptions whatsoever. There's a small caveat there. There's some way that you can jump out of an error in C, but it's not typically what you want to do. So you basically would return an error value in the return, from the function and then try and deal with it, sort of baked into the code itself, whereas Python will use the exception framework and model. I really like this. There's these high level sort of abstractions on how to think about this. And there's two ways of thinking about it, and you can start to see how C and Python take these different perspectives. So the first of these sort of high level abstractions is that it's easier to ask for forgiveness than permission, right? You've probably heard this saying before. And this is the Pythonic convention for handling errors. So for example, looking at a key in a dictionary that doesn't exist, you try and do it, and then if it doesn't work, you're like, oh yeah, shit, sorry. I promise I won't do that again, and it's fine, I'll fix it up, and then we'll keep going, right? So you try to do something problematic, and then you ask for forgiveness after. And that's the classic example, whoops, here. Fish does not exist on the animals dictionary, but you try and read it, and then if you get a key error exception, you just handle it. So basically, it's just, what this is saying is just have a handler to catch things that could go wrong. The pros of this is that it can simplify the core logic. You don't have to have lots of different, try and do this, check if it's there, if it's not there, do this, if it's there, do that. You just do it and then you handle it. But it can make code non-structured, and it can be harder to reason what code can be executed, and it might get you in the habit of just doing things and not actually thinking about what you should check, right? Does that sort of ramble make sense? I don't know what Terry Haas has sent, but YouTube didn't like it. And then the other side of the coin, the C side of the coin, I'll retract it, I thought it said restricted, sorry. The C side of the coin is look before you leap, right? So it's don't try and access the fish key. Ask the dictionary if it has the fish key. If it has it, read the key value, otherwise don't. Okay, so it's a different conceptual model of handling error-prone logic. Look before you leap. So in the look before you leap models, you don't require exceptions. Why? Because you should be asking, before you do something potentially problematic, you should be asking if it'll work. If it will work, you do it. If it won't work, you don't do it. It encourages maybe a bit more depth of thought and understanding in your programming, but it can complicate code, because you've now, instead of just being able to read a key, you've got 4 lines of, if the key exists, do this, otherwise don't do this, blah, 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 blah. You get the idea, right? But it's cool to think about these two sort of conceptual models on how we can deal with error-prone code, and it's really cool to. So this is where I always tell students, especially, but even engineers that don't really think about these things too strongly. But we talk about when we're teaching programming that programming languages don't really matter. It's the concepts that matter, and new languages will come along, and you'll be able to pick them up if you understand the concepts really well. But languages are beautiful things because they change how we think about programming if they're very opinionated. And C and Python are both examples of quite opinionated languages. And this is a concrete example about one of those opinions, right? Python is all built around this idea of trying something and then trying to fix it if it doesn't work. And that changes how you think about your problems and how you solve them. I'm not saying one's better than the other. And then you look at C, and it's got a completely different methodology of thinking. And this is an example where if you're working and you're solving a problem in C versus Python, doesn't matter that you're the same programmer solving the same problem, the language you're coding in will influence how your code runs and how safe it is and how performant it is and all of these different things. Not just because the languages might be more performant than another, but because it's changed how you've thought. And if you write a lot of Python, you're going to think like a Python programmer, and you will do things like EAFP. But if you write a lot of C code, you'll think like this a bit more. It's not to say one's better than the other. It's just a different way of thinking about it. But if you're thinking about these things, like that's what makes a really good engineer. Yeah, that's something I just want to say. We're not going through all this theory because for the sake of it, because we had to check a box. We really think that what separates a bit of a code monkey from a really good software engineer is that when you're a mid to senior to staff engineer, an architectural software engineer, a really good software engineer, you're always thinking about these things. When you decide what language to do, what framework to pick, you're not just looking at how many stars on GitHub it has, you're thinking about these sort of things. Anyway, that was a bit of a ramble. Blue Play says, not sure if this is related, but I know a lot of games have a bunch of errors and warnings when launched in the console, even though they work fine. That's a really interesting point. So why might that be the case? I'm just positing here. And I used to work with a lot of game engineers, so maybe I can even ask them. But why is that the case? Well, a lot of games, depending on the type of stuff you play, are probably written in low-level languages like C, C++. I mean, Unity is C#, I suppose, but Unreal is C++. And these are just languages that are going to have a lot of different configuration options, and so they might be sort of pushing things that cause some errors to get logged. There's also a difference between errors and warnings. Most likely, they're probably spitting out warnings. I mean, if it's really an error, if it's critical enough, the program just wouldn't run. They might be pushing the compiler and just doing some hacky things. I think that the answer that I would give, and I'm not an expert on why this might be the case, but game development is really cool because of how game developers write code. And it's very different from how I write code and how software engineers write code, because they really push performance. That's all they care about, because games really need to push the hardware, because the better something looks, the more money they're going to make, right? And they want to make these beautiful games that do amazing things. And game development is it's amazing what those guys do. And they will really hack things together to get that performance. And when you really hack things together, you're not necessarily doing things in the way that it was intended. And when you don't do things the way that it was intended, you get things like errors and warnings. Now, the game developers, if they're good, they will understand the system so well that they know that that error can be ignored, potentially, for example. Or they might not be and they've just made a mistake, right? I don't know, but it's something to think about. What's with all these retracted messages? Wesley, another one. But anyway, you don't have to feel... Oh, okay, cool. Roller Coaster Tycoon code the whole game in assembly. Yeah, exactly. Yeah, that's nuts. Same with the original Pokemon games. Those were coded in assembly. But yeah, Blue Plays, it would be cool. I'll ask an ex-colleague or something. But it'll happen not just in games, will happen in any software system that's complex enough. It's just, yeah. Okay. Brief break, not really. Let's keep going. Type checking. So this is another form of static and dynamic sort of safety quality control that some languages have different approaches to support you in writing good, safe code. So some languages have a non-optional, so I don't know why it's mandatory, built-in static type checking. The big example you'll all be familiar with in C. In C, if you want an integer, you need to ask for an integer. You get the number of bits to fit an integer in. If you want a boolean, you ask for a boolean. If you want this, you get the idea, right? The language has types available at the static processor when you compile it and at the runtime. So when the program is running, an integer is an integer, and the language knows that this variable is an integer. Some languages have optional, still built-in static type checking. The big example I'm familiar here with is TypeScript. So in TypeScript, you can ask for an integer, and you will get an integer, sort of, but you can also just ask for a variable, a dynamic variable. That's because JavaScript is a purely non-statically typed language, so you can still get access to the non-statically typed variables. And then you have languages that don't have internal type checkers. Now, a bit of a sort of, this is sort of changing for Python because there is types in Python that was introduced. I mean, it's been slowly introduced as the language has evolved over time. Now in the later versions of Python, there's some pretty sophisticated static type checking. So Python's basically becoming a bit more like TypeScript-esque. They're doing it in a different way though. Ruby's a better example. So Ruby's just got, you never really deal with types in Ruby. In some ways, it's more opinionated than Python in that way. But there are modules for Python that actually do implement static type checking. MyPy is one of them. It gives you variables with static types. So Python gives you variables. Python allows you to give variables static types, yes, but without an external checker, they're ignored. So you can just say that, you know, this value is an integer, but it's not really going to do anything with it. And so MyPy actually lets us statically type check our Python code. So here's some examples. Now I've got this open here. Let me clear this. Okay, let me make this a bit smaller. Let me do this one. All right, so we have two functions here, one called count, one called search. They accept two variables, needle and haystack. What does count do? It just counts the number of needles in the haystack. So it's just counting the number of characters, right, in the string. It's just a cute little name to call it, needle and haystack. Search is going through, so it's looping through the length of haystack. If the character matches, it returns the character itself, whereas count is counting it. Does that make sense? So search will return, in this example, well, it would return none because there's no Z, but if I put in H, it will return 2 because there's a H here and there's a H here. Yes, I know that's not how you spell Hayden. Or it could be. So we have these two functions here. The point of this, and I mean, why don't we just quickly run these? Python, oops. What did I just do then? Python, safety, yep. So you can see if we count the letter H, there's 2 occurrences, nothing mind-blowing there. And if we search it, we get back H because there is in fact a H in Hayden. Now, this is Python, right? We know that we're passing in a string called Hayden and Hayden, and we know that we should be trying to count or search for a H. But there's nothing in Python stopping us from looking for a different type, like the number 2. And when I run this, Python just says, well, there was no 2 in Hayden. Even though it's not the string 2, it is an actual integer 2. And it's not just that, this could be a list with the value H. Right? Like there is nothing in Python checking or letting us check what the types of the things that we pass into the functions is. This freedom of Python is one of the reasons Python is so popular, because we can just do stuff, and if it works, it works, and if we don't, we ask for forgiveness, right? But sometimes we want to write more safe, more secure, more scalable code, and Python does actually let us implement some static type checking in later versions of the language, and we can sort of just lightly explore that here. So what, and you'll have to bear with me a little bit, but what we can do, so if we look at search, for example, because with search, let me get rid of this. So if we do this, for example, we should get none, because none, there is no number 2 in the string Hayden. But we can actually say that, look, I only want haystack to be a string. Or is it a capital S? Okay, hold on. I might need to use the optional. I just need to go to the bathroom. Sorry, guys. Let me just quickly. I'll be a second. Okay, sorry, thank you. All right, so Alex, use str. What are we talking about here? Oh, yes. Okay, cool. All right, so what I was saying is we might actually want to say that we only want haystack to be a string. And so what we can do is we can use, whoops, let's come here. I think you're right, Alex, by the way, but here we go. So Python static types. And so as the Python language has evolved, even though Python started off as a language with no type hints and statically typed language, the demand for it sort of did arise. And so Python added something called type hints. I keep losing the tabs. Added something called type hints. So it let you just do that. It let you hint the type of the things that it wants as parameters and the types of things that a function returns. It was added in 3.5, so that means it's available in 3.7. So you can use this syntax here. Colon string, for example, returns a string. So we can come over, whoops, not that. That's the slides. We can come over to the code here and we can say, well, search, the needle has to be a string and the haystack has to be a string. And then the whole function, what does return type? It returns search returns a string. But it doesn't always return a string. It can sometimes return a none if the string doesn't exist. So I think what we do here, I don't write much type hinted Python. So I don't know how to do Python type hints optional. They might always be optional, but I'm not sure. Let's have a look. Only in 3.10 we had that. So it might just be that in 3.5 onwards, the return type could always be none. I think that's what it is. But what this is letting us do is say that search, this needle needs to be a string, and the haystack needs to be a string. And so when we're using something like search and we hit, if I can spell it, and I start coding, you can see here that it tells me needle should be a string, haystack should be a string. But I believe it's not going to actually enforce it. So if I run this, you can see that I still passed in this 2 to search, which is not a string, right? It's an integer. It's just a hint. It's just an annotation on the code base to say what the programmer intended the parameter and the return type to be. So it's a step towards a typed language, but it's not really doing anything. It's not doing anything dynamically, definitely, and it's not even doing anything statically. It's just like, the best way to think about type hints like this is that they're just like a comment saying like, oh, needle should be a string, right? So type hints are available in Python 3.5 and later. So in the 3.7 version of Python, we're asking you to use, you have access to type hints. My natural proclivities, I really like TypeScript. I like type hints in Python. I think it's better just to use them. If you're doing something really hacky and quick, you might not need to worry. If you're writing code that's going to be used by other people, I think it's always better to use the type hints. It communicates just a little bit more information about what you were thinking when you wrote the program. Does that make sense? What if we want to return an int or a string? Well, this is saying I'm returning a string. So I mean, it's returning a string here, for example. We go back to H. But again, it's just a hint. It's not really doing anything. And then I think, so to be clear, here's a few a bit more further reading, but that is the end of the lecture content. But I just wanted to go in, we've got a few more minutes, 5 more minutes really, because things end at 5 too. But I wanted to talk about some of the recent developments in Python for actual static type checking, that are, I think, starting to get a bit more popular. I know some colleagues that I used to work with in industry that write a lot of Python. They all do static type checking in Python now. And MyPy is one of the big tools to do this, but it doesn't just do type hints like we saw in Python. It actually checks the code that you pass in, for example. So for example, right, if we actually statically type check this needle, we would get an error or a warning of some description when we tried to pass in a string parameter to needle. And so MyPy is what lets us do this. So we're just going to spend 10 minutes trying to get MyPy up and running on this program to see how it can sort of help us. So let's go MyPy install. Getting started. Here we go. It requires Python 3.6 or later. That's fine. We install it like this. So you can use Python or Python 3. You should all be familiar with this stuff now. So we're installing MyPy. Okay, that's downloading and installing it, no problem. Once MyPy is installed, simply run it by using the MyPy tool. I mean, that's so simple. Now, I've never used MyPy, but what I expect is that it's going to complain to us in some description. Oh, actually, is it already? Oh, no, never mind. That's because this is a Git repo. So that's showing changes. But I would expect it to raise an error at the static checking because this is not a string. So it looks like all we do is go MyPy, this is called safety.py, and let's see what it tells us. Did I press enter? Is it slow? Okay, so it is a bit slow. I mean, this is really cool. This is telling us, right, that there's actually 2 errors. We've got to sort of be careful with what we call these. They're type errors, but they're not really like runtime errors. So these, like we ran this Python program. There was nothing wrong that, this ran, it just returned none. But if we wanted to adhere to the static type checking with MyPy, we actually have 2 errors here. The first one is the one that was the obvious one. On line 23, there was an error. Argument 1 search is not a string, it's an integer, and that's incompatible with what I said it was. Totally makes sense. this is like a compiler error in C. It didn't run the program, it looked at the code, it statically analyzed it, and it said, look, you've told me needle needs to be a string, but you've not given it a string. Therefore, that's an error. It's also said, actually, hey, on line 20, you're returning none. None is not a string. You told me that the function needs to return a string, but none is not a string. So that's another error. There's another type error there. It's an incompatible return type. Now, there is a way to say that it can return an optional string. Now, I'm just not sure how that works. So do you do... Is that how you do it? Did I just... No. My... Oh, okay, you put it in square brackets instead of solid brackets. Okay, cool. So you do have to import this optional type, and this works with the type hints as well. So the cool thing about MyPy is it just builds on the type hints in Python. So it's not actually like any extra syntax, right? You can just use it with the type hints. But now this, if we run this again, we should only get one error now. And yeah, so we get the error that the search, the needle, still should be a string, but we're not, this line 20 return type of none is no longer an issue because it can return an optional string. But can I return an integer here? What do you guys think? Is that going to cause an error? Yes or no? Echoic says, yes, this will return, this will throw a MyPy error. Come on. A couple more answers. Are we unsure? Or are we just losing interest? I mean, if you're unsure, you can just say you're unsure. So Rock Brick, you have all such interesting YouTube names. The Rock Brick says no error, interesting. Garon says no as well, interesting. Nope, since it's optional, interesting. I'm not sure if you have to declare that none is an option, but I think either way it's an error. All right, well, why don't we run it and see what happens? It is an error. Why? The return type of the function is an optional string. So it's either a string or it's nothing. It can't be an integer. That's not a string. So this would actually be an error. Exactly, Julia. Like always, Julia is spot on. Int is not none or a string. So optional is just like, so I guess optional str is just none, well, it's just an str or none. But nothing else. It can't be an integer, it can't be an array, it can't be anything like that. Ooh, excuse me. You can do sort of anything with these types. Hints, arrays. You can have the parameter types and the return types be arrays, for example. So it can be a list of integers, you know. This is a valid return type, for example. You might, in some versions of Python, you need to import it from typing. So you need to import, is it capital L? No, it's not. You import it like that, I think. It is lowercase. Here it's... Oh, it depends on the version. So I think it should be lowercase, uppercase, because that's what we import. Yeah, I don't know what the issue is here. Type hints, return list of int. Missing colon at the end. Oh, did I just backspace it? Yeah, cool. So this is now saying, okay, I want, yeah, mind blank there. I want to return a list of integers. So we'll get the same sort of error here. It was expecting a list of integers, but it didn't get it. I think you can even then say I can return an optional list of integers. I bet if it's intuitive, this is what I imagine the syntax would be, and it looks like it is. So this could be none or a list of integers, but it can't be two. It can't be a single integer, or it can't be a string or anything like that. So you can actually do, with MyPy and with the typing system in 3.5, later versions of Python, it's even more built in. You don't even need to import, I think you don't even need to import things from typing. You can have a pretty well statically typed language in Python. Pretty cool. I'm not going to, yeah, we don't have time. I mean, at the end of the lectures, we're at the end of the lecture. There's not time to sort of go into the nitty gritty nuances of typed and statically typed and untyped languages. I like statically typed languages personally. I think they make me write safer code with less errors, and it communicates more information. Whether or not you just use them as type hints, whether or not you build in MyPy into your workflow, whether or not you use other approaches, it's up to you. But it's kind of interesting, at least, this is what I'll finish the lecture on, to see that if you go back to the 70s, you had these strongly typed languages like C. You know, even C#, Java. They all had types built into the language that were enforced. You then go on to the next wave of languages, and you have things like Ruby, and you've got things like Python, and you have things like JavaScript. That at some point in the around 2010, I mean, we can actually look at this if you guys are curious about this stuff. Most popular programming languages over years. I think GitHub do a nice chart, and so do Stack Overflow. But I wanted, this is what I wanted, okay. So if we go to 2010, I can't go that far back. If we go to 2014, the top language is JavaScript, then Python, and then Java, okay, is Ruby here? Ruby's here. If we go back even earlier, so I think this is 2014. In fact, in 2014, the top language is Ruby, then it's Python and JavaScript. They're the top three languages. And they're all actually quite similar. If you look at these three languages, what do these languages have in common? Remember, this is Python. This is an early version of Python before it even had the type hints. So that's before 3.5. What do these languages have in common? Nope, I've lost. I've lost everyone. They're all high level, Zach. Absolutely. The other thing they've got in common is that they all have no static type checking. Ruby has no static types, no type hints. Python at this point in time, no static types, no type hints. And JavaScript, no static types, no type hints. This is 2014. We jump to 2021. Well, this is, I don't know how much oh, hold on. They're not all ticked. So I also wanted to put TypeScript on. Is TypeScript not here? Oh, it's there. And then I want to sort of, this isn't really the best website for it, but okay, we can at least look. What do we see here in the trends? We see Python going up, but now Python has types optionally. We have JavaScript going down 5%. I mean, that's 4.7%. Okay, that's quite significant. Why is that happening? Well, we have Java going up again, which is kind of odd, but we have TypeScript going up 2%, the largest increase year on year for any programming language in this list. And what's TypeScript? TypeScript is JavaScript with static type checking. So it's like MyPy for Python, but built into the language. And it sees the biggest jump in 2021. We see Go with an increase. Go has types. C++ is going down. C is going up a little bit, not much though. But my point is that it's sort of really interesting what's happened. In the 2010s, we have languages without types that are most popular. Now what we're seeing is a reaction to that, a response. It's the pull and the give. We have languages with optional static type checking becoming more popular. So I think like my personal take on this is that we had really strongly typed languages. Then we had things like Python and Ruby, which just had no types at all, and people actually really liked it. Developers really liked it. They wrote a lot of Python, a lot of Ruby. We came across a lot of errors and bugs. And we've come back to a middle ground now that's like, okay, types are actually quite helpful. They stop us writing some bugs. But dynamic languages are really nice to use and productive. And so, I mean, this dip in JavaScript and this increase in TypeScript, I think is the most telling sort of demonstration of this. What we see is TypeScript is almost becoming the de facto version or flavor of JavaScript. This is very interesting because TypeScript is not, like TypeScript is like an optional language, like a extension language on top of JavaScript. And it's beating JavaScript in growth. That's incredible. So I think this goes to demonstrate just how the industry is sort of responding. Anyway, I've gone a few minutes over. I hope you found that interesting. I hope you found the content today interesting and enjoyed the discussion. As always, let me really quickly get the feedback QR code. Lecture feedback, here we go. Share it, QR code. Open it here. Here we go. There's a QR code. Hopefully that works. Let me know if it doesn't. It's probably a bit big. Okay, cool. But yeah, Zach, so they're all high level, they're all dynamic. So I think, to summarize it again, high level languages are still most popular, but with some type checking is the growth. So I really like TypeScript, so you could always look into it. Anyway, thank you everyone. Thank you, Julia. Thank you, Zach. Thank you, Blue Players. Thank you, everyone else. All 30 of you, 38 of you are still here. Any feedback, lecture feedback, you know what to do. But, you know, if not, I will see you tomorrow for the second lecture. Have a great day. Good luck with iteration 3. And I'll see you tomorrow. And happy Easter, but I'll see you tomorrow. I'll wish you happy Easter tomorrow. See you, everyone. See you, Alex. See you, Felix. See you, Tan. Ciao, ciao, ciao. See you, you fun.